Welcome. Have you ever stared at a problem in your computer science class and just thought, there is no way to solve this in any reasonable amount of time? Well, you're probably talking about NP-complete problems. They're basically the final bosses of computation. But here's the crazy part. We solve massive versions of them every single day. So in this explainer, we're going to pull back the curtain and show you exactly how we tame these impossible beasts. Okay, so here's our game plan. We'll start by wrapping our heads around what makes these problems so-called impossible. Then we'll get into the fun stuff, the clever shortcuts that real-world engineers use to get around this. We'll do a deep dive into one of the most powerful tools out there, the SAT solver, and we'll even solve a problem together, step by step. And finally, we'll tie it all together with some key tips to make sure you absolutely crush your exams on this. All right, let's get right to the heart of it. In theory, if you tried to solve a big NP-complete problem with just brute force, it could take the world's fastest supercomputer longer than the age of the universe. Seriously. But obviously, we're not waiting around for that. And that right there is the central paradox we're going to unravel. So what's the secret? If it's not just throwing more computing power at it, what is it? Well, the answer is a total shift in how we think about the problem. Instead of killing ourselves trying to find the one, single, perfect solution, we use clever strategies to find a good enough solution, and we find it incredibly fast. It's all about being smart, not just strong. So let's open up the toolkit. When an engineer hits one of these NP-complete walls, they don't just throw their hands up. They reach for a set of really practical strategies. The first and most common tool in that box is something called a heuristic. The best way to think about a heuristic is as a smart shortcut. You know, imagine you're trying to get home during rush hour. You probably have a rule of thumb, like always avoid the main highway. Now, is that guaranteed to be the absolute fastest route every single time? No, but it's a really good strategy that almost always saves you time and a headache. That's a heuristic, and these heuristics come in a couple of common flavors. First, you've got your greedy algorithms. These just make the best-looking choice at every single step, and they never look back. It's kind of like packing a suitcase. You put in your most important thing first, then the next most important, and just hope it all works out. Then you have local search. This is more like you've already packed the whole suitcase, but now you're just fiddling with it, swapping a couple of things around to see if you can make it close just a little bit better. Both of these are super useful for things we see every day, like scheduling meetings or creating a university timetable. Now, if heuristics are the tolls, then meta-heuristics are like the instruction manuals for how to use them better. They're higher-level strategies that stop our simple shortcuts from getting stuck in a rut with a bad solution. And what's really cool is that a lot of them are inspired by nature. You have genetic algorithms that mimic evolution, simulated annealing, which is based on how metal is cooled to make it stronger, and even ant colony optimization, which literally learns from how ants find the shortest path to a picnic. Here's another brilliant trick. Sometimes, a massive problem is only hard because of one tiny, specific part of it, a parameter we can just call k, and if that k happens to be small, the problem can suddenly become totally manageable, even if the overall size of the problem, n, is gigantic. Look at the example on the screen. If k is something small, like 5, then 2 to the power of 5 is just 32. And multiplying 32 by a billion, that's nothing for a modern computer. This whole idea is called fixed parameter tractability. The key is to find and attack the real source of the difficulty, not the entire problem at once. Okay, now let's focus on what is arguably the Swiss Army knife for NP-complete problems, the SAT solver. This is where a lot of these clever ideas all get bundled together into one seriously powerful tool. Now, before you can use a SAT solver, you have to speak its language, and that language is called conjunctive normal form, or CNF. It might look a little intense at first, but the idea is actually pretty simple. You take a big, complex logic problem, and you break it down into a bunch of simple or statements that all have to be true because they're linked by ands. The real magic here is that a huge range of real-world problems, from circuit design to scheduling, can be translated into this one standard format. So how in the world do they work so fast? Well, it's a whole cocktail of smart techniques. They explore the possibilities systematically with something called backtracking, but the real secret sauce is in the other tricks. Unit propagation sets off this amazing domino effect of logical deductions. We're going to see that in just a second. And clause learning is incredible. It basically gives the solver a memory. So if it goes down a wrong path and hits a dead end, it learns a new rule so it never makes that same mistake again. Theory is one thing, but let's actually make this real. We're going to walk through a small SAT problem right now together to see exactly how these principles work. This is how a solver really thinks. Okay, here it is. This is our formula. Our mission is to find a combination of true or false for the variables a, b, c, and d that makes this whole thing true. And remember that little and symbol means every single part in parentheses has to end up being true. All right, let's start by just making a choice. Let's just guess and say A is false. Now look at that very first clause, A or B. If A is false, the only way for that clause to be true is if B is true. It has to be. So our one little guess has immediately forced a second decision. That's unit propagation in action. The dominoes are starting to fall. And the chain reaction just keeps going. We know B is true, so now look at the third clause, not B or C that becomes false or C, which means C must be true. And following that same logic, the fourth clause, not C or D, becomes false or D, which forces D to be true. Do you see how that one simple guess just cascaded through the whole formula, making most of the decisions for us? Now if our first guess had led us into a corner, a contradiction, the solver would just backtrack, undo that guess, and try something else. And it would use clause learning to remember, hey, don't ever make that specific sequence of choices again. But in our case, we got lucky. Our guess was good, so all we have to do is check our work. Let's look at the one clause we didn't use, clause 2, not A or C. With the values we found, that becomes true or true, which is true. Perfect. Every clause is satisfied. We did it. We found a solution. A is false, and B, C, and D are all true. All right, we've gone through the theory, and we've gone through the practice. Now, let's pull it all together and really focus on the key things you need to know to lock this stuff in for your courses and, of course, your exams. First off, why should you care about any of this? Because SAT solvers are quietly running the world. They're used for everything from verifying that the microchip in your phone doesn't have any bugs to complex AI reasoning to logistical planning for shipping companies. The ability to translate a hard problem into CNF and just hand it off to a super-optimized solver is a real superpower in computer science. Now for the exam itself. Your professors will often drop clues and keywords in the questions. Think of this slide as your secret decoder ring. If you see the phrase, can be verified quickly, your brain should immediately scream NP. If a question talks about the hardest problems in NP, that is the literal definition of NP-complete. Learning to spot these cues is honestly half the battle. Let's just lock in these core definitions one more time as simply as possible. P means we can solve it fast. NP means we can check an answer fast. NP-complete means it's one of the hardest problems that's still in NP. And NP-hard, well, those are even tougher. They're at least as hard as anything in NP. Feeling a little fuzzy on all the terminology? That is completely normal. I've got a super simple memory trick for you that's going to help you keep all of these complexity classes straight, even when you're under pressure in an exam. Here it is. Just burn these 4 short phrases into your brain. P solves fast. NP checks fast. NP-complete is the hardest of the checkable problems, and NP-hard is the hardest overall. That's it. If you can remember that, you can reason your way through almost any question they throw at you. So at the end of the day, what's the big takeaway from all of this? The theory of NP-completeness isn't a stop sign. It's really a signpost. It tells us when we should probably stop banging our heads against the wall, searching for a perfect, fast algorithm, and instead start getting creative. Real-world algorithm design is the art of using all the tools we talked about, heuristics, approximations, randomization, to tackle these impossible problems every single day. And that's a wrap. You now have the fundamental toolkit for understanding and actually approaching some of the hardest, most interesting problems in all of computation. So the last question is for you. Now that you have these tools, from optimizing the entire internet to cracking complex codes, Which impossible problem would you try to solve first? Thanks for joining me.